Hi everyone, Mr. Neighbor here, and we're going to finish up with power before moving on to machines. So, last problem on power. Two physics students, Ben and Bonnie, are in the weightlifting room. Bonnie lifts the 50 kilogram barbell over her head, approximately 0.60 meters, 10 times in 1 minute, or 60 seconds. Ben lifts the 50 kilogram barbell the same distance over his head, 10 times in 10 seconds. Which student does the most work? Which student delivers the most power? Let's look at work first. So if we look at the work equation, that's all about force parallel over a certain distance or displacement. So to lift the barbell, they need the same amount of force because the barbell is 50 kilograms for both of them. They're both lifting it the same distance over their heads. So when these two quantities are the same, that means the resulting quantity of their product will be the same. So who does the most work? They do the same work. The next question talks about power. So which student does the most power? If we look at our power formula, it is work over time. We just realized that the work was the same for both. So this number is the same. The time, however, is different. Here we have 10 seconds for Ben and 1 minute for Bonnie. So if you divide a number by 10 or a number by 60, which is going to come out the bigger result? The one that's divided by 10. So that means Ben is going to have a larger power because we're dividing by a smaller number. We're breaking it into less pieces. We're breaking it into 10 pieces versus 60 pieces. So who delivers the most power? Ben. So there you have it, work and power. All right, now on to machines. So what is a machine? A machine is any device that changes the size, direction, or distance over which a force acts in order to make work easier. So simple machines that we will be dealing with are a single lever, wheel and axle, pulley, wedges, a screw, or an inclined plane. Sometimes gears are lumped into there. A compound machine is a device containing two or more simple machines working together. So these are the 6 simple machines we're going to be working with in this chapter, and all their machines are comprised of these. So when you have a machine, it gives out a certain mechanical advantage, a benefit to using that tool. If it doesn't benefit you in some way, make it easier in some way, why use it? Tools are there for a reason, to make things easier. So the mechanical advantage measures how a force is amplified by that tool. Okay, so if you get out the same work as you put into the object, this would be a mechanical advantage of 1. It doesn't help you at all. If you get out a mechanical advantage greater than 1, that means the work you put in, you got more work out, which is what you want. If you have a mechanical advantage that is less than 1, that means you put in more work to do a little bit of work, which you don't want. So it's calculated by taking the output force and dividing it by the input force. I have a hard time saying that word. So you could think about it like this. Typically, I write it like this over here. The units are both force, so when you divide a Newton by a Newton, the Newtons cancel out and you're just left with a number. So it doesn't have a label, no labels. All right, first example. Keisha applied 20 Newtons of force to turn an ice cream freezer crank. The crank's output force was 60 Newtons. What was the mechanical advantage of the crank? So we take the output force divided by the input force. So when we do that, we get out 3. So the force that you're getting out is 3 times as much as you put in, because you only put in 20. A pulley is used to raise a heavy crate. The pulley is such that an input force is 223 newtons, is needed to provide an output force of 1,784 newtons. What is the mechanical advantage of this pulley? So our output force, what we get from it, is this much, and what we input is 223. So when we divide those, we get 7.93 approximately. So almost 8 times the amount of force that we put in. That's great. That's what we're looking for when we are having a machine, a big mechanical advantage. Now we move on to efficiency or mechanical efficiency. We were dealing with mechanical advantage. Now we're talking about efficiency. So efficiency measures the amount of work that is used and not lost as heat or friction. So a good machine should have an efficiency as close to 100% as possible. But unfortunately, no machine will have an efficiency of 100%. It will never be greater than. Our goal is always to get a machine that's 100% efficient. All the energy we put in, it gives out that same amount of energy. The problem with machines is that there's friction, and friction rubs against things, and that produces heat. That's energy. That energy is lost then to the bigger system, goes outside the machine into the world. So we lost that energy. So now our efficiency is not 100% anymore. That's why we use things like oil. So we don't have as much friction and heat loss. So we have more efficiency. So efficiency is calculated dividing by the work output, by the work input, and then multiplying by 100. So mechanical advantage, you divided the out by the in. Same thing here, the out by the in. But now we're not dealing with force, we're dealing with work. Sometimes you'll see mechanical efficiency or efficiency with this letter right here. That's a Greek letter. That is a lowercase eta. So that's written out in English, ETA. Kind of looks like an N, but it's said eta. So this was a percent that you're getting out. How much are you efficient? And it comes out as a percent when you do it. That's why we multiply by 100. So as I was saying, in an actual machine, the output work is less than the input work because of friction. So the top number of the equation is always going to be less. Our goal is always to increase mechanical efficiency. So there's a couple ways to do that. Really, it goes under the broader term of reduce the friction. So for example, you can use ball bearings or oil to reduce rolling friction. If you have slippery materials such as Teflon, you can reduce the sliding friction. And if you make things more aerodynamic, with the shape it's made, you can reduce air friction. So all these techniques are ones that help make your machine more efficient by reducing friction. So there's less and less energy loss with heat or friction. Alice and Jim calculate that they must do 1,800 joules of work to push a piano up a ramp. However, because they must also overcome friction, they're actually doing 2,400 joules of work. What is the efficiency of the ramp? So the mechanical efficiency is the work that you get out, which really you're just moving this much, but you have to put in this much to overcome the friction. So when you divide that out and times by 100, you would get out 75%. So it's 75% efficient. It takes 1,200 joules of work to lift a car high enough to change a tire. How much work must be done by the person operating the jack if the jack is 25% efficient? So not very efficient. Let me change colors here. So mechanical efficiency is equal to your work out divided by work in. We know the efficiency is 25%. So times 100 here. So 25%. Your work out must be